Welcome, everyone, to this webinar titled The Importance of Annular Sealing in Geothermal Wells and Well Integrity. The series is brought to you by the GEODE consortium, which is led by Project Interspace and the Society of Petroleum Engineers, and funded by the U.S. Department of Energy's Geothermal Technologies Office. My name is Haley Allen, and I'm your facilitator. Please note we are recording this call and we muted all lines. Today's event will last up to 90 minutes. We encourage you to ask questions throughout. Simply click on the Q&A button at the bottom of the screen. It is now my pleasure to welcome our moderator, Catalin Teodorio. Dr. Teodorio is a professor of petroleum engineering at the University of Oklahoma-Norman, Oklahoma, and holder of the Milborn Chair of Petroleum Engineering No. 6. Before joining the OU, he was an assistant professor at Texas A&M and head of the Drilling, Completion, and Workover Department at the Clausthal University of Technology, Germany. He has more than 25 years of experience in the petroleum industry and academia, with key qualifications in research in drilling and production equipment, drilling technology, integrated computer-aided analysis, well completion, testing of the OCTG, design of downhole and surface equipment, software development, EOR geothermal wells, and in the design of laboratory-specific equipment, i.e. high-pressure testing, large-scale testing equipment for multi-phase flow, and drilling process simulation. He specializes in developing new threaded connections for the OCTG and is an expert on drilling problems and failure analysis. Some of his recent research areas at the OU include the largest drilling vibration setup worldwide, the development of a cement repository for the long investigations, as well as geothermal well construction and well integrity, and the development of complex mechatronic systems designed to support AI and machine learning applications. He is the author of more than 360 publications, of which more than 85 are peer-reviewed articles and 2 book chapters. He was awarded, among others, the SPE Drilling Engineer Award, an outstanding reviewer for SPE journals. He is also well recognized for delivering customized industry courses covering drilling, completion, well integrity, and geothermal topics. I'll turn it over to you now, Catalin. You're on mute.
Thank you so much, Haley. First of all, I would like to thank GEODE Consortium for their support to develop this event and making possible, the share of this knowledge worldwide with everyone. And I'm very pleased to introduce our speaker, Iosafat Esquiti. Iosafat is the Senior Business Development Manager for WellTech North America, based in Houston, Texas. And he is the focal point for deepwater projects in the North America and Caribbean region. In 2019, Iosafat expanded his role to include clean energy projects, focusing on geothermal and carbon capture and storage initiatives across Americas. Over the years, he has contributed to several papers in the oil and gas and geothermal industry as both primary author and co-author, and he is an active member of SPE, GRC, IEDC, and AD. I will not spell all the names there, but Iosafat, you may begin and enlighten us with the well integrity talk today.
Yes, thank you very much, Catalin. Thank you, Haley, and thank you to GEODE. So as Haley and Catalin mentioned, my focus today is to talk about the importance of well integrity in both oil and gas and geothermal wells, and the different types of annular sealing systems to achieve this well integrity for life of well, and what's the importance and what factors to consider during the selection of these systems, and at the conclusion, talking about the best practices. So I hope you guys can see the screen here. So we'll start with well integrity. So what is well integrity? Well integrity refers to the ability of the wellbore to contain fluids and prevent the uncontrolled release of these fluids or gases in the annulus or in the bore to surface or within the subsurface formations. And this is important to maintain this well integrity throughout the life cycle of the well. So it's not only important when we're drilling and completing the well, but throughout the entire production phase while we're producing these wells, during workovers when it's turned back into the drill and complete team for repairs and workovers. And finally, during abandonment, it is critical to have a good well abandonment for environmental purposes and making sure that the wells are sealed for life. So well integrity encompasses the technical, operation, and organizational solutions that are employed to manage the risks associated with the well construction, the well's operation, and finally the well abandonment. So when we are planning the wells, we have to always consider this portion of the well integrity as one of the most important throughout the life cycle. So on a typical well construction, you have the conductor casing, the surface casing, one or multiple intermediate casings, and finally the production casings. And these casings are often isolated by an annular sealing system, whether it's cement or different type of mechanical barriers. You have to effectively seal these annular sections, and this will allow you to have a good well integrity throughout the life of the well and beyond during abandonment. So it is important to understand the downhole conditions and every single aspect of the well during the well construction to basically consider and select the right materials for isolating the annulus, such as cement or these mechanical barriers, and also the type of muds and brines that would be in the well. So the types of annular isolation systems, we'll talk about multiple different ones here. The first one and most common one is cement. So the cementing process refers to the process of placing cement slurries into the wellbore annuli, uh, either from the toe of the well all the way up to surface or covering certain sections of the well. And these slurries have to be designed to basically cure and harden and create a strong impermeable bond between the casing and the formation and the rock, and sealing the wellbore and isolating the different zones across the reservoirs. The cement slurry often consists of several components, which is the powder itself, different additives, and as cement technologies have advanced, there's a lot of different materials that can be incorporated in the cement, such as polymers or microspheres, fibers to make it more compatible, in example for geothermal wells. And the precise composition of the cement is critical for the well's conditions in order to have a proper seal. Now, when we talk about cement, we got to think that this is a life of well solution, and cement is a lot of times degradable. So there are some challenges, and we'll talk about these challenges later here in the presentation. So this is the primary and most common type of cement barrier or annular barrier. But then there's also other type of barriers, which include packers and mechanical barriers, annular casing packers, that combined with cement or standalone can bring a lot of benefits into having a life of well integrity. So talking about the different type of annular isolation packers, we have the well-known swellable packers. These are used to isolate mainly wellbore sections in the open hole. And these type of packers rely on a chemical reaction between the fluid of the well and the rubber that the packer is made out of. So it's basically an absorption process where the fluid is absorbed by the elastomer. The elastomer grows volumetrically, and when this elastomer grows, it then reaches the rock face or the previous casing, and it creates the seals across the annuli. These elastomers are a volumetric expansion, and they rely a lot and are heavily dependent on the downhole conditions of the fluids and of the temperature. So selecting the soluble packers is an very, I would say, technical process that needs to take place. And if the right conditions are not there downhole, the packers may not operate as intended. The other type of packers are inflatable packers, the well-known ECPs, external casing packers. And these are tools, again, to isolate the wellbore. These are packers that are inflated via surface pressure, and they basically have a bladder system that holds the pressure inside. And this bladder pushes the elastomer out and creates the seal against the borehole. So this type of tools are mainly used for temporary isolation. They are again are suited for downhole conditions, but depending on the temperature and the pressure, they may be heavily affected. So this both soil packers and inflatable packers for very high temperatures have some challenges. So when selecting this type of tools, it's important to select the right tool for the downhole conditions. So once the packer is inflated and expands outwards, then the fluid is trapped in that bladder, and basically once it's trapped in there, it creates that seal. So that fluid that is trapped in the bladder is very critical to maintain the packer integrity throughout the life of the well. The third annular packer here are the mechanical packers. There are both mechanical packers for open hole and case hole applications. And they are typically run as part of the casing string, and they're hydromechanically activated. So basically you apply either pressure or weight, and then the elastomer is compressed and it seals against the parent casing. And some of the open hole isolation packers, mechanical isolation packers in open hole, when you basically compress them, that rubber element extrudes and tries to seal against the borehole. There are some challenges and some restrictions with this type of packers, especially on the expansion ratio that they have due to the conformance to open hole sections where there might be rugosity, ovality challenges to seal against. But they are typically run also with cement in combination with cement to help cement isolation. And the last one I'll talk about is the metal expandable packers. These are basically similar to the inflatable packers in the how they operate and how they work. Basically, you apply surface pressure, and as you apply that pressure from surface, you basically start expanding the packer out and creating a seal against the formation. What is very good about this type of technologies is that because it's a metal packer, it's good for withstanding high pressures and high temperatures, and is suitable for various downhole conditions, not affected by fluid conditions and by temperature and pressure. So and the fluid is not trapped in the system, so it's not dependable also on that fluid being trapped to create the seal. So these are the different type of isolation systems that exist for annular isolation. Again, cement being the most common one utilized. So now let's look at what type of challenges exist during this annular isolation and why it's so critical to select the right type of isolation, but also do a combination of these technologies in order to have a life of well solution. So regarding cement specifically, there's multiple challenges that exist. There's challenges when it comes to life of well sealing, when cement is often basically subjected to different temperature cycles and pressure cycles, and then the cement gets basically exposed to those pressures and the expansion and contraction of cement, often leading to cement failures. And these cement failures can create crossflow, can create basically different pressure communications between tip zones or under pressure formations, gas migration through the annuli, ECD challenges, basically when you're pumping that cement job, if the cement job is not planned properly and your column of cement is too heavy, you might induce losses in the well. So there's this ECD that is very critical, and also something that is very important during the well construction is the casing eccentricity. So you see on this picture here, basically where this was an offshore well where the section of the well was pulled out of the well, section of the casing was pulled out of the well, and you can see that in different annuli, there's basically no cement or uh, very bad cement quality in some sections. You can see on the very last one here, uh, this eccentricity of the casing basically creates this unremovable mud when you're pumping the cement that doesn't allow this to be displaced out, and then you have this whole channel to have gas migration or potential fluid migration. So eccentricity plays a big role. Um, so this challenges often lead to annular crossflow from basically this cement being challenged by the fluid placement and having those channels. And this annual crossflow, in some cases and in geothermal wells, can be very often seen that it can lead to casing corrosion and casing challenges. So it's very critical that crossflow is basically stopped and maintained at the reservoir section. Compromise cement quality. So again, especially when you're doing multiple frac jobs and you're doing stimulations, the cement gets shattered, and then you start having this microannuli and channels that gas can migrate to surface, leading to annular pressure buildup or sustained casing pressure on surface. And finally, this cement contamination from either a water migration or gas migration into the cement while it's curing. And when this happens, then that once the cement is cured, you still have those challenges presented in the previous slide. So it's very important that when we are using cement for the well integrity purpose, we select the right properties of the cement for the application, and often combining it with other technologies uh, brings a lot of benefits. Now, when we talk about isolation, and let's say in open hole where you don't have cement, there's also multiple challenges that need to be addressed. These challenges is borehole geometry, especially in open hole. The rugosity and ovality of the open hole is very critical to take into account when trying to seal an open hole section. The open hole diameter and washouts. We often see washouts when we're drilling the wells. So it's important that whatever we use for sealing can take that expansion and use the seal the washout. The high differential pressures and high treatment pressures across the different sections. And when we're not using cement, that cement helps us to anchor the casing in the well. We have to consider the high axial forces. And I'll talk about it a little later, but basically when we're considering the open hole isolation, the axial forces that are acting on the different packers is very critical to analyze and make sure that those components can take those loads. And finally, the formation properties, such as the type of formation, the rock strength, and whether the rock is homogeneous or not. It makes a difference when we're isolating these zones. So during the well construction, and it's very important to make sure that we've selected the right technologies, we set them correctly, and then we are able to effectively eliminate cross flows, eliminate channeling, and then have a true well integrity throughout life of well. So talking about geothermal applications, more and more we're talking about enhanced geothermal systems where you have multiple clusters similar to what we have in the shale and unconventional reservoirs. And maintaining this isolation, it becomes very critical, such that when you inject through one of the wells and produce through the other, you have the highest efficiency and don't have losses across the different wells. So it's important to understand those challenges, do your risk analysis, and then while you're doing the well planning, and then select the right well construction elements. So kind of a summary of the key isolation challenges: maintaining well integrity, uh, ensure the right barrier and robust barrier is in place to prevent the fluids, making sure that you have an effective way to remove the mud. So effectively removing the drilling mud will help you achieve a better bond in case of cement is used, and getting rid of that mud, like I showed you on that image. That mud cannot be moved out, and then you have basically a channel through it. Uh, the ECD challenges: equivalent circulation density management, making sure that you plan for either one or multiple cement stages if needed. And if you don't use cement, then making sure that the circulation pressures with your annular barriers are not affected when you're cleaning the well, making sure that you don't induce losses. Uh, Addressing the narrow pressure margins, more and more as you're drilling wells, you have very narrow pressure margins, and you're sometimes leading with less than 1 ppg of margin between the frac gradient and being able to control the well. So it's important to plan your fluids properly, but also make sure those fluids again can be removed while cementing. And maintaining the zonal isolation during the well intervention is also very critical. So we plan a well, we construct a well, and we plan it to produce and be productive for 20, 30 years. So we have to think realistically that we are going to intervene the well sometime in the future. So making sure you have that isolation for running in during intervention is important. Um, and some specific examples of these challenges is mud channels in horizontal wells. Trying to get rid of that mud is very, very difficult when you're pumping on an extended reach horizontal. So you have to plan for this. Loss circulation, ECD limitations, again, talking about those challenges and potentially inducing losses. Um, Making sure that you account for those pressure differentials and depleted reservoirs, and again, coiled tubing zonal isolation. So it's important that we recognize these challenges and plan to address them in advance. So things to consider also when you're selecting the annular sealing technology. Of course, you have to go through a process. You look at the available technologies that are in place. You do a screening process first. You see all the available technologies are analyzed based on the well conditions. Then you basically discard and check the ones that are good for those basically those conditions, and do a selection of the most appropriate technologies based on the technical and safety features. Then you go to a detailed review and perform a more in-depth analysis, basically in detail risk analysis of the criteria of the well, and then you come down to the conclusion of what is the best technology to operate in that condition and in that well, and you select that technology. It's always important that when you select the technology, you also have some kind of contingency or backup in case the plan is not performed as intended. So in terms of well conditions, you look at the application and identify the specific purpose of the annular seal. And when we say this, it's important because the annular seal may be very critical to prevent sustained casing pressure, or it may be very critical to prevent crossflow across different zones. It may be critical to isolate water. So it's important to identify the specific purpose, uh, identify the restriction and IDs. More and more wells are being drilled with very slim casings designs, and this, for example, in cement is a challenge because you have a very, very thin wall of cement. And the thinner the wall of cement, the more easy it is for contamination, and the more difficult it is for placement. So looking at those restrictions is important. And when you're running any type of annular packer, you do have some restrictions there to consider while running in hole, and also making sure that you don't search the well. And those type of analysis are important to consider. Doing a well cat analysis, and performing a torque and drag with the different components is critical. So you can do that with all the modeling tools that exist in the industry, and that will basically give you an idea of the basically the feasibility to run that technology or not. The pressure and temperature that the packer or the casing or the cement needs to withstand is critical. So we're selecting the materials capable of withstanding the very high pressures and high temperatures, especially in geothermal wells, is of most critical aspects of the well construction. So choosing those technologies and making sure you do that risk analysis and go through the selecting process is important. Long bearing movement and dynamics. So evaluate the actual loads that the casing will be subjected to throughout the life of the well, and making sure that whatever you choose to seal is able to take those loads and basically provide that annular sealing throughout the life of the well. And finally, fluids and chemicals, also same or as important as pressure and temperature, is what are we going to be basically exposing our components to. Sometimes you have very corrosive environments downhole, and you can have H2S, CO2, very corrosive brines, or you may have acids that you're going to pump. So making sure that all those factors are considered during the selection of the process is very, very critical. Another thing that we need to consider, and this is more for open hole completions where cement is not there, is understanding the downhole forces that the open hole systems will be subjected to. And especially like in geothermal wells with EGS, or in unconventional wells where you're going to be fracking multiple zones, you're going to have effects like ballooning effect. And this ballooning effect will create some residual forces, and some of the residual forces will basically work against each other and don't have an impact on the packer, but then you'll have other ones that will have an impact. So considering this ballooning effect on the casing and what that ballooning is reflected in terms of actual force is important. You have residual loads of setting packers when we're isolating with external casing packers, whether it's an inflate or a metal expandable packer or a mechanical packer. You have some residual loads that are acting on it, and some of them will have an impact to the packer itself. One of the most critical things we need to consider in both oil and gas and geothermal wells is the thermal contraction of the casing. As you cool the wells down, especially on geothermal wells where you have very high temperatures, you'll create a thermal contraction with a very large delta T. And this thermal contraction leads to potentially multiple feet of movement across the casing. So again, selecting the right technologies to withstand that movement, and also to also compensate for that movement is very, very important. Pressure stimulation, when you are stimulating the wells, again on EGS applications in geothermal, or when you're doing this unconventional, or even on conventional wells where you're stimulating, you have a piston force that is created by the stimulation itself acting on the packers. So it's important to ensure that that is isolated properly. If you are pressurizing against the sump, Uh, this axial force that's created here is acting on a very large area, and this very large area can create a massive amount of actual load or force acting on the packer. So it's important to do those calculations. So taking into consideration all these different basically conditions and these different effects that will happen during the life of well is very critical. So what this is just an example. So a packer needs to provide sealing to the rock face and provide high anchoring loads. Uh, we have to do this and provide high differential pressure ratings across the different zones, depending on the treatment pressures and depending on the depleted sands or depleted pressures that you'll see. You have to be able to isolate in unwashed out or irregular shaped holes. And finally, the whole purpose of this is to have an isolation of over the life of well, withstand the multiple temperature cycles that you'll be subjected your well to, uh, and then have a robust and successful well construction. And finally, about centralizers, it's very important to centralize the casing where you're running in hole, and a lot of times the casing is not centralized, especially on highly deviated or horizontal wells. It's very difficult to centralize it. So this is kind of the profile here that you will see when you have uh, no centralization. So the basically the casing will be touching at different parts of the well, and this will lead to challenges. So when you have a concentric well, very centralized, again, you're pumping cement, and your cement fully has a uh, even distribution of cement across the different area. When you don't have that, then you have eccentricity, then it becomes very challenging to have a good isolation with cement. So again, combining the cement with other technologies helps a lot, and also using centralization properly helps a lot. You also have to consider that the more centralizers you use, the more rigid the string may become. So there's a balance on centralization, but making sure that you have the proper centralizers in place will aid on good well construction. So talking about additional challenges that we find in geothermal. So cement failures of thermal cycling loads, again, it's very common to see this in geothermal wells. So these large temperature changes will exert high stresses and loading to the cement in the annuli, and this will basically have failure of cement. This happens during production near the surface, a stimulation downhole, during pressure testing of the casing, and during basically workovers and recompletes or sidetracks. So this mechanical failure will lead to loss of basically production, basically to having to shut down the wells. So um, this will basically affect your well's economics, and in worst case scenarios, it will have environmental impacts where the environment is basically affected. So from unwanted fluid gas or fluid migration or production, uh, surface bend flow or casing pressure to surface, basically emitting gases on surface. So it's very critical again to have the proper isolation. So this is another example of cemented casing with different concentric strings or eccentric strings, and you can see the effect of this while you're cementing. So these are other challenges that you see in geothermal wells. So making sure that you predict the failure of cement during loadings is important. You have to consider the wellbore geometry, the casing thickness, the temperature or pressure changes, the formation mechanical properties. And then there's a lot of softwares in place that will help us predict this failure. And once we take into consideration all the softwares during the drilling, completion, stimulation, and production phases, we'll be able to have a better understanding of what we need to put in the well to achieve that well integrity. And finally, in enhanced geothermal systems, uh, they could be high temperature geothermal or low temperature geothermal, but we definitely are subjecting the well to multiple stages of stimulation. And during this high pressure stimulation or fracking, uh, you are basically shattering the cement, making it weaker and potentially creating flow paths of the fluids or gas to migrate. So combining the technologies and combining like the metal expandable packers, which are suited for very high temperatures, can often lead to a successful and more productive well, both on oil and gas and geothermal applications. So what to consider when we're selecting the annular sealing technology? And I'm putting here the comparison of the metal expandable packer, the inflatable packer, and the soluble packer. We have to consider the life of well sealing, right? So the components that the packer is constructed. So it's metal, uh, basically life of well. Yes, it may be even more suitable than or have higher properties than the casing. So an all metal sleeve will always be more reliable for life of well sealing than elastomeric components like the bladder or the soiling compound. Not trapping fluid, especially on those geothermal wells, is very critical, because this fluid trapped in those chambers of the packer will basically have very high uh, delta T's across the life cycle when you're cooling the well and heating it back up. And this trapped fluid basically will convert into basically, as you heat it up, you're gonna basically increase the pressure inside that packer and potentially burst it. So making sure that you don't have trapped fluids is very important. Uh, that the delta P and the differential pressure that the rating of the packers maintain over the expansion ratio is very critical. So if you have washout formations or you have irregular geometry, you want to make sure that your packer can withstand that differential pressure that you need and that your packer is rated to, even setting in washout formations. Robust construction to allow it to rotate and work the string down when you're deploying, especially on horizontal wells. A lot of times you need rotation. You're floating the casing in, so making sure that you can push that casing and don't damage the elements while you're going in hole. Make sure that it's not affected by downhole fluids. And again, the main importance of this is to maintain life of well integrity, right? So you want to choose the right system to be able to maintain that integrity throughout the life of the well. So I'll talk a little bit about the metal expandable packer technology that is suitable for geothermal applications and is one of the unique technologies that has been qualified and tested to geothermal conditions. So this metal expandable packer is basically a packer that is an external casing packer mounted on a casing string. And through surface pressure, you put pressure into the casing, pressure is diverted into the packer. And as pressure goes into the packer, it plastically yields the metal, conforming the metal to the different sections in the well. Basically, whether it's open hole or case hole, it will conform to the entire surface of the well and create that annular seal. And then once it's fully set, then the communication from the board to the annuli is closed. And then the communication from the upper or lower annulus is enabled to go into the packer chamber. And this, what it allows it to do is not have this trapped fluid inside the system, So when you're stimulating the well or going through the different temperature cycles, whatever pressure is in the system, whatever highest pressure, whether it's on the upper annulus or the lower annulus, that pressure will be maintained inside the packer, both energizing the packer to seal against the formation, but also preventing any collapse happening from the packer. This technology, when it was tested to geothermal temperatures, it has multiple of these sealing elements, and each one is a redundant element. So one seal making full contact will be able to withstand the delta pressure that we need. But in this case, you have multiple of these seals as a redundancy, especially in open hole applications where you need redundancy. For geothermal applications, it's been qualified to 6,000 psi delta P. And for other applications, it can go up to 15,000. So it's a very unique technology that can be utilized in geothermal wells, either in combination with cement or in lieu of cement, and just have a open hole isolation. So this is a little bit how the system works. It has the valve system incorporated in the packer itself. And then this valve will basically, when you're running in hole, pre-expanded, you basically are running whole. You're not prone to premature expansion because you need a high pressure to plastically yield the metal. So it's a high differential pressure across the packer. Once you have that high differential pressure across the packer will expand. And once that expands, then this packer will seal the communication from the bore to the packer, and then that compensation system will start acting in place. And one very important thing to highlight, so all the oil and gas, we know that the American Petroleum Institute, the API, has very strict standards such as the ISO, and these standards are put in place to make sure that when a technology is qualified, it meets the standard to be deployed in the downhole conditions. So the metal expandable packers are a technology that are qualified under API 11D1 standard. And this standard is the standard used for basically downhole packers, both in open hole and case hole. But in this case, case hole is the primary of the API 11D1, but the metal expandable packers are basically qualified to this more strict standard than the API 19OH. And one very critical thing to say is that these packers, when we're talking about geothermal, they are basically exposed to steam, and the packer has been successfully qualified in conditions where steam has been built up due to temperature, and basically converting that trap water into steam, and it has been successfully qualified. So some solutions for well integrity, again, when we're talking about aiding cement, is running this technologies with cement. And as they are run with cement, you can expand them as soon as the cement plug is bumped. You basically expand the packers in green cement, displacing the cement across the face of the packer, and the packer creating a seal against formation. This can be both in open hole and case hole, and you can have one or multiple of these packers in place, basically isolating different zones or isolating a challenge zone, like you can see on this solution here. And it's a fast and high expansion solution from surface. And once you expand it and you set it, it's basically done. So the other application for geothermal wells is when you don't use cement in the production interval. This would be kind of an EGS application. You can use the packers to isolate the different zones. And between the packers, you can have some kind of basically injection sleeve, or you can have pre-perforated pipe, or you can come and perforate afterwards. basically you have the true isolation with the MEPs, and then you can have the treatment across the different sections of the well. And coming back to the closing remarks and conclusions, I think breaking old habits is very important these days. I mean, wells are not what they used to be. Uh, and I think both oil and gas and geothermal companies must embrace innovation. And when it comes to well integrity and annular isolation, use the best tools that are out there to construct the wells. Uh, the future of our generations is important. So making sure that we build these wells such that they don't create environmental challenges in the future is very, very important. So uh, yeah, I encourage uh, all the companies and the service companies and all of us to look for best practices. There's a lot of technologies that have innovative solutions, so look at them and adopt these technologies. The ultimate goal is to have long-term sustainability and make sure that again us and future generations have the best way forward. Uh, some remarks here on poor well integrity pose a significant technical challenges throughout the well life cycle. So if you do have that poor well integrity, you are going to face the state casing pressures, which you then need to mitigate, remediate, and those are very costly. And in worst case scenarios, you can have disasters of contamination in basically the oceans or land, and this can become very serious. Uh, when you have annular pressure buildup and you don't protect it properly, you will have downhole, uh, basically challenges with burst or collapse casing. As more complex well designs are being done, we have to make sure that we apply the best technologies out there to have these designs uh, be successful. And aging infrastructure is also critical. There's many existing wells that are designed for different conditions, utilizing older technologies, and they face the risk of corrosion, erosion, barrier degradation over time. So it's important to choose the right materials. So finally, safety is the most important one of all, I think, safety and environmental impact. So we want to prevent blowouts and uncontrolled releases from they pose significant risk. We want to avoid any leaks and uncontrolled fluid migration to surface or gas migration to surface that can contaminate groundwater, surface water, or the environment itself, the air we breathe. And when it comes to the economics, when we are facing these challenges, companies often face multiple financial challenges trying to fix these environmental impacts or safety impacts on these wells. So again, adopting the right solutions, I think, is the path forward. Using technologies like the metal expandable packers to aid on the well integrity will definitely be an advantage. Using advanced cementing systems, more and more cements are being developed with special polymers, especially for geothermal, and trying to be able to work better in high temperatures, but also enhancing the zonal isolation by a combination of the technologies of cement and technologies of the annular sealing systems will definitely be the best way to construct a well and have a group that understands well integrity and do well integrity management throughout the life of the well. So with this, I conclude my presentation. I hope it was informative for the audience, and we are open to questions now.
Thank you so much, Josaphat. Now it's time for question and assuming we're going to have the answers, so we're going to provide the answers. So if you haven't already, use the Q&A section or the Q&A button on the Zoom. Please use that and state your question. I will read the question and then we're going to go for the answers. So I will, give a few minutes to you guys online for stating the questions while I will try to state a question for Josaphat first. So on these, complex, topics about well integrity and particularly delivering, customized tools for the industry, do you think that the current standardizations will need upgrading? We need to move on specific standards for, well, let's say, oil, gas, geothermal, CCUS, or we need one standard to rule them all?
That's a good question, Kathleen. I think as we address CCS, for example, I mean, there's a lot of, I think a lot of the critical part on carbon capture and sequestration is that CO2 exposure and how the different metals and the different elastomers will basically behave over time. So I personally think that having standards for CCS and geothermal is important. But you may give your contribution because you may be more of an expert on that. What do you think?
I mean, generally, standards, they are always derived by the industry needs to have, reliable tool and products. And usually, if we look historically for the, what you presented on Parker standards, they evolved from a very simple, pressure testing of that tool to a much more complex, like gas testing and then cycle testing and so on. So I do expect that sooner or later the industry will move towards to have this standardization adapted for those new, let's say, elements. So particularly CO2 as well as geothermal, specifically where thermal cycles probably will be one of the key elements on that.
I agree.
So I'm still waiting for questions to be able to read and so on. Meanwhile, just a reminder that there will be a QR code at the end, and you all are welcome to take the survey that will be presented to you there. I will just continue with a little bit of the question that I do have and some of the work I've done in the past. So whenever we talk about life of the well, the biggest challenge we have today is that actually we do not know the time of that life of the well, whether it is, I don't know, 100 years, whether it's 1,000 years or only 10 years. So with respect to all these tools and so on, how do and you have the experience from the industry, how do industry try to cope with long-term achievements of these tools?
Yeah, so one of the things that we do is aging testing. So when you are basically developing the technology and qualifying it, there's different ways to accelerate aging of the technology or of the component, and that way we can try to emulate 25, 30, 35 years of exposure to downhole conditions and be able to qualify it to the standard to meet those conditions. So this can be from going to hundreds of cycling across the system to exposing it to different fluids at different temperatures during the testing. So that's one of the ways we try to achieve that longevity of the tools.
Thank you. We have a question online. So I will read the question. I'm curious to know, how does the metal expandable packers guarantee the well seal in an open hole completion mode? Specifically, I mean, could rugosity or ununiformity of the well bore affect the sealing?
Yeah, so the metal expandable basically expand with pressure, and as you apply pressure, there's no moving systems in the packer itself that basically expanded, let's say, in a cylinder way. It's more of a growth of that metal and adapting to the rugosity of the casing. So the system has been qualified to up to 1.2 ovality, and it's also being qualified in different chambers with let's say bugular formations, so that we know that packer will conform to the borehole and create the seal. It has a limit of how much it can expand, but as long as we're within that limit, we will be able to create that seal. So that's why measuring the washouts is critical to understand what's the limit on the washout, and make sure that the packers are suitable for sealing.
So this is another excellent question. How many metal expandable packers found application in geothermal wells so far?
Out of the top of my mind, I would say we've done, especially in the Asia Pacific region, we've probably done like about I would say 15 to 20 wells where they have been utilizing geothermal wells, and yeah, that would be the kind of the amount so far.
So you think that metallic packers, so packers with no elastomers, whatever the design is, do you think that that could be the new key to unlock geothermal potential?
It's definitely a critical component to unlock, I think, I would say economical geothermal, especially on those CGS wells. But I would say that ironically enough, the metal expandable packers that have been deployed have been mainly deployed in conventional geothermal, where it's high temperature geothermal. So, but definitely it's a tool that enables that longevity of the well. So I do see it as a enabler for a better a better economics for geothermal.
So it looks like we have one more question. How resistant are the packers when you produce and inject in the same well?
Yeah, so because I mentioned that compensation system that exists on the packer, whether you put it on production or injection, uh, as long as the packer that is selected is rated to the pressure that is going to be injected or produced through, going through those temperature cycles in production and injection will not affect the sealing capability, because the packer will always be in what we call an injection mode, taking the highest pressure into the packer. So we just need to select the right pressure, let's say rating, and the right seals for the temperature, whether it's all metal seals or non-elastomeric seals for geothermal.
Thank you for that. I'm just checking if further going.
I see there's one more question, Kathleen.
I don't see it. Oh, yeah. Can you combine these type of packers with a gravel pack or
And
screens?
screens? Yes, yes. So we've done multiple wells with screens with the packers in place. I would say this is more oil and gas applications. I've never done anything like this on geothermal, but oil and gas, we've done quite a few wells with screens systems and frac pack systems, but we also have a capability to run with a gravel pack with a shunt tube system in place. Yes.
Okay. So since eliminating elastomers from the sealing component of a packer could open a new door for high temperature. What's your opinion about super hot and extreme high temperature? So if you remember Iceland, for example, we're targeting 500 degrees Celsius as a temperature on that. Do you think that some of these components may have a chance to withstand these high temperatures?
Yes, I think it's a combination of the temperature and the actual loads that are going to be subjected to. But yes, I think especially the non-elastomeric or all metal seals, I think they have the potential to be successfully qualified to those high temperatures. Right now, the highest I know is being qualified is 330 degrees centigrade. But there has been some modeling to 450 degrees centigrade that is looking to be very promising. So yeah, super hot rock, high temperature geothermal. I think this type of technology will help definitely uh, better construct the wells.
So I know we've been talking a lot about packers, as with respect to oil and gas, geothermal, CCUS. But in your opinion, what else do you think we need, particularly for geothermal, outside the packers and better casing design in order to unlock this energy?
I know there's a lot of work on cement blends that are higher temperature, which I think eliminating cement in a lot of instances can be done, but there are probably some instances where they cannot be completely eliminated. So those cement blends that have higher temperature capabilities are critical. I think other enablers for EGS applications are production sleeves that are also high temperature to allow shut off and opening of sections. Uh, and the other technologies that I think have some challenges still are drilling technologies. So there's definitely things to work on the drilling technologies that will enable especially super critical geothermal. I see one more question there, Kathleen.
Josaphat, can you please advance to the last slide where the QR code is, so the audience can start the survey on that? You should have your last slide with the QR code.
I don't think I have the QR code
Just
here, sorry.
advance to the last slide.
I think that was the last slide. I don't think it's there, Haley. I apologize.
Okay.
I don't think it's there.
Okay. Meanwhile, there is one more question here, which so if recovery of the completion become necessary, is it possible, or could you explain what the withdrawal procedure will be, with respect to this type of metallic packers that we've been discussing here?
Yes. So they are non-retrievable systems because as the metal cold works and expands, it actually gets hardened and it's difficult to retrieve. So yeah, I guess the answer to retrieving a completion, they can probably be dragged out in a case hole completion. If they're in open hole, it would be almost impossible to retrieve them.
Thank you, Safat. For the audience, now you can see the QR code, and please feel free to scan this. You'll be redirected to a survey, and we'll appreciate your input. This survey will just make all the GEODE series webinar better for the future, and so on. Okay, more question, guys. I'm very much interested to see your feedback on that. Of course, I do have a lot of question for you, Josafat, on this, but I'm still checking, the questions. So you mentioned several times CCUS and the application of that. Since the packers you mentioned are actually permanent packers, it means that you have to install them when you drill new wells. So this type of application of the tools will be always necessary for the new wells. Do you think that that may lead to a new well construction concept, your well construction design for the future? I'm just thinking about, for example, the class 6 CO2 wells and so on. Do you think that these new type of packers and particularly annular well integrity may lead to another class well, let's say class 21 well?
Yes, I honestly think it can. CCS, and I think I'm not an expert on CCS, but I know that the annular sealing in CCS it's very, very, very critical, especially when you're trying to sequestrate that CO2. So we've seen in different nations with operators and workshops that there's a lot of challenges with the materials in place, right? So making sure that those tools are actually tested under CO2 conditions with impurities, and making the environment corrosive, and testing those tools to corrosive environments is critical. So I do believe that if not lead to let's say a new class of wells, it will definitely help on uh, improving the sealing and the annular integrity in the existing let's say classification. So definitely is a good implementation to those type of wells for long term. And when we talk about CCS, it's not only about 20 or 30 years, they're talking about 1,000 years, right? So be able to sequestrate that CO2 for 1,000 years as a minimum. So I don't know if the casing will last 1,000 years or anything else will last 1,000 years, but we definitely can try to put the best materials in place to achieve that.
So yeah, I'm just still checking the questions roster. You also have a discussing here, and I will try to look a little bit more on geothermal. And I would like to see a little bit of your experience of moving from oil and gas to geothermal. So first of all, what was kind of the driver of trying to adapt for geothermal? And the other one is, do you see a much faster in the future transition from let's say all the knowledge that oil and gas industry have done it to be much easy and faster integrated into geothermal? What's your opinion on that?
Yeah, I guess to answer the first question, I mean, the company I work for and the previous companies I work for, I mean, being able to have a technology that can cross from an industry to industry is important. So when we started looking at this metal expandable solutions for geothermal, it kind of was an easy transition from what we had in oil and gas in terms of having a system that is metal for geothermal made it kind of an easy transition, more than CCS, for example, because CCS, again, you have to consider all the corrosive environments. So we looked at how we can help the geothermal industry. I mean, we want to not only contribute to oil and gas, but also to new energies. And being able to have a technology that has been proven and it works in very harsh environments in oil and gas, it was kind of a good incentive to say, okay, let's now try to get the same results in geothermal. Also, I think the support from the Department of Energy, specifically on developing these technologies, has really pushed for a lot of the service companies to try to uh, either come up with new ideas or use the oil and gas technologies that they have in their portfolio and extend them for geothermal. So that answering the first question and kind of answering the second question, I think we have a lot in common between oil and gas and geothermal. Um, I see more and more synergy and more adaptability from the geothermal community to use oil and gas technology, which I think is great. I think probably decades ago, I was probably not involved in any of that, but I can feel comments where there was a kind of a separation between geothermal and oil and gas, even though it has so much in common when we talk about drilling a well and constructing a well. So the fact that there's a lot of these groups like GODE and a lot of these different initiatives to uh, don't start from scratch and use the technology that has enabled the success of oil and gas into geothermal is critical. So I'm all for that, Kathleen. I think we have to keep pushing and encouraging all the companies that have innovative solutions to cross over and help the geothermal community.
Great. And I can't stop asking now, what would be your advice for the future generation, for the young, engineers, for the students that will be about to become the young engineers? Should they just focus oil and gas? Should they try to expand their knowledge? What's your advice for that?
No, always expand the knowledge. So uh, I'm an electrical engineer, so and I've been in the oil and gas industry for 21 years now, and I've been fortunate enough to be exposed to geothermal early in my career. So I've been exposed to geothermal wells probably for more than 15 years, and uh, being able to understand a little bit of that area has really helped me not only in my professional development but also understanding the what we need to do to make our planet more sustainable. So definitely I encourage all the students and the young professionals out there to be always open to learn. Also, I would encourage not to be close to oil and gas because there's oil and gas is a very important industry for us. So be open to both and also be willing to be in learning mode throughout your entire career because we always learn every day. So that's what I can advise.
Well, that sounds fantastic. Don't forget, guys, questions, are still allowed. Use the Q&A button to ask that while we are talking a little bit more about particularly, geothermal on that. And one of the things that I was, kind of really curious, because you presented here, and I was trying to link this also geothermal as well with oil and gas, is that a lot of packers in general, they're typically limited to dogleg severity and particularly to short radius wells and so on. And we know that one of big concept in geothermal will be horizontal wells, short radius wells, so very complex wells in terms of geometry. So in how far the packers and probably some of the projects you've been involved, you've seen this wellbore path and radius curvature radius of the well will push to the extreme this type of tools, packers in general.
No, that's a good question. I think, as you mentioned, the horizontal wells and those short radius wells posed a challenge not only to the components like packers, but also to the casing itself. So one of the things that we have to consider and we have to try to achieve is have a slim design that can be run, but also have a design can be worked down when it's deployed. So that is why for us it was so critical to work on a system that you can rotate, reciprocate the string down, and also don't be very long, but don't also be very short that you create a very stiff system, right? So there is a balance to evaluate there, Catalin, on let's say clearance between the packers or any technology that you're running in a well and the parent casing or the borehole, and also using software that exists in the industry that is been developed for that specific purpose, trying to understand the torque and drag when you're running in, making sure that you run as a realistic completion in your modeling as you're going to be running in your well, such that that modeling is predictable enough and you can have a better higher chance of success. So we have to take advantage of all that modeling and also the e-learning. I mean, you're an expert on that, Catalin, so I can't talk much about it, but I know that as we have more and more data available for us, using that data is important to understand the past experiences and learn from those. So and adapt the technology to be able to uh, account for those challenges that were encountered in the past. So also you using that data to implement new ways of doing things is important. And I don't know if you want to comment more on that, but I think it's critical to use the immense amount of data we have in our favor.
Well, data means a lot of deployment of the tools in general, and one of the things I hope to see from the industry is that the more tools will become deployed, also the cost of this deployment will go down, enabling, particularly for geothermal, lowering the cost of well construction and well completion is a major goal of almost every attempt in a geothermal project for that. But one thing that I would like to comment, and please feel free to let me know if I'm correct here, is that currently in the standard packet testing, the V0 to V6 type of testing and so on, there is very little discuss or mention about the dogleg severity and testing of, let's say, a packer under, let's say, bending conditions. I spend a lot of time working with connections, and when we test a casing connection, we usually also include the bending as a main load for the system in order to prove that connection will withstand the downhole conditions, in those wells. Have you seen, customers or have you seen other, companies that are pursuing, particularly operators that will ask about let's test, packers and downhole tools under bending conditions?
I have, and we've actually done it for a couple of operators in the North Sea. And this is they again have very short radius and very high dogleg severities. We're talking about 15 degrees per 100 foot dogleg severities, and where a conventional product will not pass through. They had multiple attempts, so we have done that. I think it's something that as wells become more complex, it's gonna be more and more needed. So yes, I think there's nothing on the standard, as you say, to test that, but there are operators that are asking to do the test on that condition. So yeah, we have done it, and it's something that is doable for sure.
So it looks like it's always important to have all the parties involved on that. It's the manufacturer, it will be the operator, the one that knows actually where to put the tool, and so on. So yeah, that's very interesting. We just got a new question here. So when considering axial loads caused by differential pressures, approximately how much resistance to sliding will be provided by the metal expandable packers?
So that's I guess, a very broad question because it depends on that differential pressure. One thing that this type of technology, the more pressure you have in the system, like the more differential pressure, the higher anchoring capacity that the packer has. But there is, of course, a physical limit to it. But we have increased the capacity of the actual loads by adding this metal expandable sleeve. If you put two or three in tandem, then you can duplicate or triplicate the actual capability of the packer itself. So we would need to evaluate the condition of the well, and then we would evaluate if we need one sleeve can take all of it or we need multiple sleeves. But just to give you an example, one of these packers can potentially take 300, 400,000 pounds of actual force. And when we put two or three in tandem, we can potentially reach actual forces of 1.2, 1.4 million pounds. So it really depends on the application, but it's kind of tailored to the application.
Very interesting. So after the question, there was a small comment on that. They said that the large movement of the packers could create inclined buckling as well as compression loads within the casing up to the next packer position. But you already mentioned by doubling or adding tandem packers, then that would solve the question here.
Yeah, when we select the packer, we don't want it to move, because once the packer moves, it can lose the seal, and then the whole purpose of the packer is to seal, right? So we always try to configure the packer and design the
Thank you.
packer
So
such that it
in an
will not move.
ideal case, let's say we don't really have any limitation on that. How many packers do you think a well we have? And I'm trying to bring here up, if you remember, the full pack bottom wall assembly, where people will put as many stabilizers as they want just to keep it, the bottom wall assembly going straight. So in terms of, well integrity and so on, what will be the packers? So can we go to have all the way packers, or you think that that's not really, useful?
No, I think it is. It depends on. I think it depends a lot on the goal and the application. But for well integrity purposes, we may have packers positioned across different sections of the well, and that may be sufficient for well integrity purposes. But when you come to, let's say, zonal isolation and production of or injection on different sections of the reservoir, we have deployed the systems with up to 200, 250 continuous meters of packers. which basically replace cement completely. And then you perforate through the packers and you can produce or inject through the packers. So the versatility of these technologies are very wide. So the amount of packers for a well construction can vary from, I would say, minimum quantities of 2 or 3 per section to couple hundreds of them, depending on what the objective is.
Thank you. Any further questions?
I think we're probably past the time.
I know I'm checking
Very
the time
close.
too, but looks like no further questions on that. But definitively, we have a hot topic today, as usually in the GEODE series of geothermal. Everything seems to be hot in here.
That's a good way to put it.
Okay, one more question. Looks like. So the question is that usually running packers require many safety measures to ensure success of the operation. And one example here is that many operators will restrict the running speed in the well in order to run those packers. What is different when we talk about these expandable metal expandable packers in this case compared to a conventional packer?
Yeah, I think when we compare it to a conventional packer that is prone to preset, our running hole speeds are much higher. Usually, and this comes really more from an oil and gas perspective more than geothermal, because again, we've done a handful of geothermal jobs, but we've done basically hundreds of deployments on oil and gas. We're usually, or the metal packers are usually not the restricting factor on running hole speeds. There's other components in the wells that are the restricting factor, but we most of the times we are I would say 1.2 to 1.5 higher running hole speeds than conventional packers. And this has to
Thank you
do
so much,
also a lot with the
Yosabat.
clearance. Yeah.
Thank you so much. Excellent topic for today, and I think now I know it's a hot topic, but we have to come to an end. So I will give further to our host Haley. Haley.
Thank you for attending today's webinar and for all of your participation. Today's program is copyrighted by the GEODE Consortium, which is led by the Project Interspace and the Society of Petroleum Engineers and funded by the U.S. Department of Energy's Geothermal Technologies Office, with all rights reserved. Have a wonderful day.
Right.
Bye-bye.